Swayam Prabha. Digital India. Educated India.
Welcome viewers to the second lecture of the course Metal Cutting and Machine Tools. So, last day we had discussed about different types of manufacturing processes which help us in attaining our desired shape and size on a particular part. So, we take a blank piece and on that we apply some manufacturing processes with the help of which we attain the final shape and size. So, among these processes we identified metal cutting or material cutting or material removal by its special characteristics, that it removes the material in the form of chips, okay, and it employs a powered device or powered equipment which is called a machine tool. We also came across the idea of the cutting tool, which is the active element which actually removes material from the workpiece. So, we have the workpiece or the part which we want of a definite shape and size. We have the cutting tool which actually removes material from this from the blank to attain the final shape or the part, and we have the machine tool which holds the workpiece and the cutting tool securely, rigidly, and provides relative motion between them in order to remove material. The machine tool also has other functions. So, let us first discuss something about the basic relationship between machine tools and cutting tools, and then on to the geometry of cutting tools. So, today we are going to discuss geometry of single point turning tool. Okay. So, first of all, on the screen you can see the shape of a single point turning tool, okay, SPTT. So, this is considered to be as the basic cutting tool or cutting element in machining. All cutting tools can ultimately be related, okay, to this particular single point turning tool. That is, all cutting tools can be ultimately shown to be composed of different single point turning tools or a modification of the single point turning tool. So, what do we see here? On the surface of the turning tool, we have first of all let us see the back portion of the turning tool. So, this is the shank or the base or the rear portion of the tool which is held on the machine tool. If we can hold it on the machine tool, it will be securely placed in position with rigidity. On the front of the cutting tool, we have three main surfaces or planes. These are called the rake surface, the auxiliary flank and the principal flank. Flank means side. So, these are the sides of the tool, this is the top surface of the tool, the top surface is called rake surface or face. Okay. So, the machine tool holds the tool workpiece pair rigidly and provides relative motion between them. The tool that we saw just now is held on the machine tool. Examples of machine tools are lathe, milling machine, shaping machine, grinding machine, drilling machine. Let us have a quick look at some of these machines. So, for that, let us select the whiteboard. On the lathe, what kind of machines do we have? Rather, sorry. Yes. So, on the lathe we have the basic workpiece. Okay. It is held securely on a device called a chuck or center. So, it is holding on to the workpiece. This one is made to rotate. Okay. It has ultimately connection with something called headstock. This headstock will typically contain gears which can change the speed of this workpiece, I mean speed of rotation of this workpiece. So, on this workpiece we have, maybe it is held on a center on this side. Okay, we have headstock just like that, we have tailstock. And where is the tool figure? The tool is brought in. Okay, I am drawing it, sorry. I will just repeat those: workpiece, work holding device, headstock, tailstock, basic body of the machine, the lathe bed. On that there is a sort of saddle which can move this way, that way, and the tool is typically held on this saddle, I mean carriage. So, this is the lathe bed, this is the tool. So, just see, I am going to make the workpiece rotate and the tool is going to move this way, and therefore, it primarily describes a helix. Okay. The tool describes a helix like that, because rotation is combined with longitudinal motion, and we can make smaller cylinders with the help of this particular device. Okay. So, if we return to the what do you call it, the PowerPoint presentation slides, lathe looks like that. What does the milling machine look like? We will be discussing milling machines in more detail. So, milling machines are machines in which the cutter rotates. On the lathe, the job rotates generally and the cutter moves either axially or at an angle to that particular rotating job. On the milling machine, the cutter generally rotates and the workpiece moves past the cutter. The workpiece might also rotate, but in general, shaping machine, the cutter reciprocates and removes material from the workpiece. So, this way there are different machine tools, we will take them up in more detail later on. Coming back, to our tool now, the initial way in which we can refer to the tool is the tool in hand system. So, if we take the tool in our hand and we move it this way, that way, there are some things which will not change. What are those? The rake surface will not change, the principal flank and the auxiliary flanks, they are not going to change. What is going to change? Well, the angles which these planes make with the different directions, for example, the x, y, z directions, etc., those are going to change. So, in the tool in hand system, these are fixed. So, these are basically, surfaces or planes. What is the rake surface? The rake surface is that over which the chips flow. This is the rake surface, and on the lathe it is placed in such a way that over the rake surface the chips will be flowing. This is the principal flank. It faces the unfinished part of the workpiece, and this is the auxiliary flank which places which faces the finished part of the workpiece. Okay. So, these are the definitions of these three planes. So, after that we come to the definition of the different edges which are present and the different points. Once we have two planes intersecting, their intersecting edge can easily be identified, and here we have identified the intersection between rake surface and principal flank as this line, this red line, and we have named it as the principal cutting edge. In the same way, the rake surface and the auxiliary flank will also have an intersection, and that is called auxiliary cutting edge. Why do we name these things as cutting edges? This is because they are involved in the removal of material by providing a sharp edge. Okay. So, there are in the single point turning tool two cutting edges. One is the principal cutting edge and another one is the auxiliary cutting edge. And when all these three planes meet, they define a point which is called the tool nose. Okay. This one is the tool nose. So, if we draw the tool with relation to the job, it would look somewhat like this. Just a moment. Yes. We are looking at the tool from the top. Therefore, this is the rake surface. Where is our job? The job is on this side. It is rotating. The tool is moving this way. So, the chips are going to come out, as we saw the last day, the chips are going to come out here, over which the chips flow, the rake surface. Okay. And this is the finished part, this is the unfinished part. So, the principal flank is on this side. We cannot see it from the top, but it is there. It faces the auxiliary flank, we cannot see it from here, but it faces the finished part of the workpiece. And we can draw dotted lines, of course. So, this is the auxiliary flank which we cannot see from the top. Okay. And this is the principal flank. This one also we cannot see from the top, but it is facing the unfinished portion of the workpiece. So, this gives us those names, and as you can see, the principal cutting edge is this one. So, it is in contact with the workpiece and its main the main geometry element responsible for cutting of the metal. Here also some cutting takes place. Here some cutting takes place and this is the auxiliary cutting edge. Okay. So, now let us move on to our next discussion. So, we have identified rake surface, principal flank, auxiliary flank, cutting edges, 2 of them, etc., in the tool in hand system. Now, let us go on to the tool when placed in a coordinate system, the machine coordinate system, and once the tool is placed in the machine coordinate system, it starts having a relationship with the different planes. Okay. So, this is our tool. What is this tool doing? The tool is having the 3 planes attached to it. These are the 3 directions: z axis, x axis, y axis. What are these planes? These planes are basically planes which define the space in relation to a machine. For example, suppose this is fitted on a lathe. So, this will be the feed direction, longitudinal feed direction. This will be the direction of the velocity vector, okay, provided the tool is placed correctly, and this one is the transverse direction of the machine. Okay. Just now that the figure that we drew, there you can easily find out these directions, and corresponding to these directions, if we combine them in pairs, we get planes. So, the machine horizontal plane is the horizontal plane. Okay. It is basically the xy plane here. If the velocity vector is correctly in the direction of z axis, in that case the machine horizontal plane gets a name called reference plane. Reference plane is defined as the plane perpendicular to the velocity vector. So, if this is the direction of the velocity vector, then xy plane is the reference plane and it will be called pi r. Now, what is the machine longitudinal plane? It contains the direction of feed and the z axis. What is the machine transverse plane? It contains the transverse axis, the y axis and the z axis. Okay. So, they will be cutting the tool along different planes and defining different angles. So, let us see the angles which are created by the intersection of these planes with the tool. First of all, I am seeing the tool here from the top. Okay. This is the tool from the top, and all angles and planes and edges etc. are defined in this system of machine reference. It is called the machine reference system. Okay. Machine reference system, and the American system of tool nomenclature uses these angle definitions. In what way? For example, if you are cutting the tool along this particular line, if this is the xy plane, okay, this is the projection in the xy plane, the plan view. Okay. Here, if you cut it with this particular plane, now you will say, what is this plane? What is this plane? This is the machine transverse plane. So, the machine transverse plane, which is pi y, I cut it and I get a section of the tool and I draw that section here. When I am drawing this section, 2 angles appear and I name them gamma y and alpha y. You might say, what are these angles? Okay. I can formally define them, but let me give you a basic idea. They give the slant of the rake surface with reference to the pi xy plane or the reference plane. That means, if the velocity vector is correctly in the I won't say correctly, if the velocity vector is exactly in the z axis, the pi xy plane becomes the reference plane. Reference plane is defined as perpendicular to the velocity vector of cut. So, if velocity, sorry, just one moment. If the velocity vector is exactly perpendicular, sorry, if it is exactly in z axis, we will have the reference plane equal to pi xy. So, we will formally define gamma y as back rake, and it is the angle between the rake surface and the reference plane in the machine transverse plane. So, gamma y is defined as the rake surface and its back rake angle. Gamma y is defined as the back rake angle, which is the angle between the rake surface and reference plane, rake surface and reference plane in the pi y plane. So, this formally defines the back rake. Now that we have defined back rake, we can define other angles very easily. Alpha y is the angle between, if you notice, this is the trace of the cutter in the cutting tool in the pi y plane. Okay. And which part of the cutting tool? This is the flank surface. We cannot see it here. We cannot see it in the plan view, but it is hidden. So, here clearance angle, back clearance can be defined as the angle between the principal flank and this particular plane. What is this plane? This plane must be pi x plane, okay, trace of the pi x plane, okay, in the pi y plane. So, angle between two planes, which are these planes? Principal flank and pi x plane, and this and it is considered, this angle is considered in the pi y plane. Okay. So, this way we are going to define each and every angle to be between two planes and on a particular, considered on a particular plane. For example, say I am defining gamma x. Gamma x is given a name side rake. If you notice, I have defined all the angles here. Side rake is defined to be the plane between the rake surface and the reference plane, okay, considered in the pi x plane. So, this way we can define each and every angle. Moreover, in the plan view, okay, in this view where we are looking at the tool as seen along z axis, we have two angles defining the positions of the cutting edges. Phi s defined as the approach angle and phi e defined as the end cutting edge angle. Approach angle, sometimes it is called side cutting edge angle, and this one is end cutting edge angle, these two angles. When we have defined these, then the tool is defined with its relation with the three machine reference, machine planes, reference planes. So, generally let us see how we can completely define the tool in the ASA system. Okay, for that, in the ASA system, in many literature, it is given that the tool can be completely defined by this particular nomenclature: gamma y, gamma x, alpha y, alpha x, phi e, I think it is phi s, phi e r. We will check this up. R is the nose radius. Now, I would not like to follow this particular nomenclature, because as you would see, there are certain problems with this. For example, there is no information about the auxiliary flank, and secondly, we might have problems with such definition if we use alpha y, alpha x together. Okay. So, we will know about these angles, but we will not accept this as a standard nomenclature for a cutting tool, because it might lead to problems. I will tell you what the problem is. Problem is this: if I define gamma y and gamma x, it defines the rake surface position in space, defines rake surface. Rake surface becomes invariant. Okay. If I define alpha y, alpha x, the principal flank becomes invariant, that is, its position orientation is fixed. So, the orientation of the rake surface is fixed, the orientation of the principal flank is fixed, and therefore, their intersection, which is the cutting edge, that will also be fixed. You cannot have a free definition of the cutting edge after this. Cutting edge is fixed, which means phi s is also fixed. Phi s is fixed after this. So, in that case, we cannot freely define phi s. That is, if I say, let us take a tool with 15 degrees, gamma y 15 degrees, gamma x 5 degrees, alpha y 10 degrees, alpha x 5 degrees, phi s say 25 degrees and phi e 65 degrees. No, phi s will be pre-decided. You cannot assign a particular value to phi s just like that once you have defined these 4 angles. So, though in many literature the nomenclature of the ESA system is given this way, we are not going to follow it. We will accept that the ESA system uses these angles, but the nomenclature of the tool in the ESA system, okay, we will not adopt this one. Okay. After this, so this way all the angles can be defined. We are not going to go through all the definitions, but all these definitions can be obtained this way, that is, we take 2 planes, find out the angle between them in another plane, okay, and our basic definitions start from the velocity vector of cut. So, let us have a look. Velocity vector, can it really change? Suppose we are having this as the tool, sorry, this as the workpiece and this as the tool. In that case, the velocity vector will be directed this way. Now, suppose someone puts the tool by mistake at a lower height, suppose this is the tool. You have a problem. In that case, the velocity vector is this way, and all the tool angles will be changing because the reference plane is now here. Previously, the reference plane was here. Reference plane pi reference or pi r. This is the reference plane now, because it is always perpendicular to the velocity vector. That is a problem. So, we always start the definition of tool angles from the velocity vector of cut. So, the American system is not the only system. There are other systems which have been formalized, and let us have a quick look at those. Another one is where the cutting edge, the cutting edge forms the basis of the definition of the geometries, that means the angles and the edges, etc. So, whenever we have cutting edge or rather cutting plane based system, we call it the orthogonal rake system. What is it? It basically defines a coordinate system where the planes are defined with relation to the cutting edge. In what way? Here we have something called just a moment. Here we have something called the cutting plane. What is the cutting plane? The cutting plane contains the cutting edge and also the velocity vector. Velocity vector of cut is here, and therefore, this is the cutting plane. What is the orthogonal plane? Orthogonal plane is perpendicular to the cutting plane and it is perpendicular to the reference plane. What is the reference plane? Just to remind you, reference plane is perpendicular to the velocity vector. So, this is the velocity vector. If it happens to be along z axis, matters are simplified. This is the reference plane which becomes pi xy plane only. The cutting plane contains the velocity vector and the the cutting edge, and the orthogonal plane is perpendicular to the reference plane and perpendicular to the cutting plane. So, we have these definitions: reference plane, cutting plane, orthogonal plane. And let us see, just a moment, how the sections come out to be in that case. The sections, I mean the angles. First of all, if you look at this figure, this is the cutting edge. Once again, this is the cutting edge. Where is the cutting plane? The cutting plane is appearing as a line here. It cannot be seen from the top. As it is a vertical plane, it cannot be seen from the top. But here it is appearing as this is the trace of the cutting plane. Then what is this section? We have cut it here. Sorry, I have not given the name of this sectioning lines. So, we have cut it along this line. What is this line? This is the trace of this is what the orthogonal plane looks like, pi o. So, this being the orthogonal plane, the section which is obtained on the orthogonal plane looks like this, and the angle between the rake surface and the reference plane in the orthogonal plane is called gamma o, or orthogonal rake. In the same way, the same section will be producing a relation between the clearance angle, relation between the principal flank and the cutting plane, principal flank and the cutting plane measured in the orthogonal plane once again. So, that is why this pi o has appeared here, and the two angles of cut are shown on the two sides. One is orthogonal rake and another is orthogonal clearance. So, if you ask me, Acha, how is orthogonal clearance defined? It is defined between this plane, which is principal flank, and that plane, which is cutting plane, and the whole thing is measured or considered in the orthogonal plane. That defines orthogonal clearance. On this side, if we look at the tool, no section is required, we are simply looking at the tool and drawing a view, and we may see that the cutting edge actually it's inclined. It's inclined, it's not straight. Here it's looking straight, but from the top, as it goes backwards, it might be inclined downwards, or it might be inclined upwards also, but it's basically having an incline. It's not moving, horizontally here. This is reflected in this view, captured in this view. It's inclined from the nose. So, if it is inclined, in that case, this angle of inclination is given a name called lambda. How is lambda defined? Lambda is the angle between the rake surface and the reference plane measured in the cutting plane. Okay? It is the angle between the rake surface and the reference plane measured in the cutting plane. Hence, this way we come across inclination angle. So, lambda is called inclination angle. It is also a type of rake. It is also a type of rake angle. So, inclination angle is understood, orthogonal rake is understood, orthogonal clearance is understood. And in this system, instead of referring to the approach angle or the side cutting edge angle, we define an angle called principal cutting edge angle. Principal cutting edge angle, just 90 degree minus phi s, and we still have the end cutting edge angle as phi 1. Okay. So, we learn of different angles in the orthogonal rake system. All right. So, after learning about this, mind you, you might say you have not mentioned anything about the auxiliary flank. On the auxiliary flank also we can make a section like this perpendicular to it. So, we will have auxiliary cutting plane, we will have auxiliary orthogonal plane, they will be forming similar angles like auxiliary orthogonal rake, auxiliary orthogonal clearance, etc. I have not drawn this on the same figure because it will turn out to be confusing if I start giving all the details in the same figure at one go. So, I have only given you details about the principal cutting edge and its associated angles. I am sure that you will be able to find out similar angles for the auxiliary cutting edge if it is required. How do we define them? Just like alpha O has been defined here, we have alpha O dash also, the auxiliary orthogonal clearance. Okay. How do we define this system? Let us have a look. We can define it this way: lambda, gamma O, alpha O dash, phi 1, phi r. You might say, isn't the same problem that you mentioned about ASA system going to occur here as well? No, because here you will find that we are defining the rake surface orientation by these two angles. We are defining the principal flank by this one. You might say, can the principal flank be defined completely this way? Just a single angle is there? Well, some information is going to come from this one. Okay. For example, with these, suppose I define the rake surface with these two, and on that I define the principal cutting edge. So, I use up this information. So, this one is oriented in space, the rake surface. On that I use up this information to draw the main cutting edge. From the main cutting edge, okay, in this direction I get the incline of the principal flank. I cannot see it from this side. I get the incline of the principal flank by this angle. So, I use this up also. Now, I find out the I made a mistake. Phi is used for getting the inclination of phi. Just a moment, let me rub off some of those unnecessary lines. What is this one? So, phi is used. So, I am sorry, let us remove this first. Phi is used up to define the principal cutting edge, and after that I define the inclination of the principal flank by alpha O, and therefore, I define the principal flank as well. So, principal flank is defined, rake surface is defined, principal cutting edge is defined. After that, alpha 1 helps me define the auxiliary cutting edge position. You know, rake surface is not just this this square, but it is it's extended to infinity in all directions. It is an infinite plane. From there we are segmenting small portion of it. So, this is the auxiliary cutting edge, and in the same way we define the orientation of the auxiliary flank by using up this information. And see, now that we have got this particular shape, and of course, you know, the rounding of this point is defined by r. Now, we have used all information to get the complete picture, the three planes that we had talked about, and hence this definition is all right. This string or this nomenclature of the orthogonal system is all right. So, we will discuss other aspects of tool geometry in the subsequent classes. Thank you very much.